Started. Okay, so acoustic emission is a somewhat more recent form of non-destructive testing, and one that is seeing a lot of development. There's a lot of interest in it due to particularly the use of composites in the aerospace world, but also it's seeing a lot of interest in the like civil engineering and transportation, other areas of transportation, because of its ability to be placed what's called in situ or installed, essentially become a system on another component, like a bridge, sensors permanently installed on a bridge or on the aircraft that can do real-time monitoring for things like in-service condition to look for impending failure. So what is acoustic emission? It's another sound-based, and it does work in the ultrasonic range, just like ultrasonic testing. But what happens with acoustic emission is, so the definition of it is generation of transient elastic waves produced by sudden redistribution of stress in a material. So what that breaks down to essentially is some kind of an external stimulus, a change in pressure, load, or temperature, is going to cause a change, a physical change in an object, and the stresses from that will show up in a release of energy. And that energy typically is an ultrasonic wave. And then we're going to sense that change in energy, and most commonly is a piezoelectric sensor, similar to an ultrasonic transducer, actually construction-wise almost identical. But where in ultrasound, ultrasonic testing, we put a sound wave into an object, and we listen for its return, or we listen for it to pass through the object. In the case of acoustic emission, is the object itself is going to be producing the sound wave, the ultrasonic wave, and then we're going to use a sensor that can detect it, a transducer or a receiver. It's technically not a transducer because it's not going to transmit, but a receiver that can detect that sound that's generated by something. So you've all done composite projects, right? Did anyone take your composite project and do anything like this to it? No? Anyone been to a composite project? The one I wish I had, when I was in college, I worked in a ski shop. And for anyone that doesn't know, a ski is made up of layers of material. Metal, wood, fiberglass, carbon fiber, Kevlar, right? It's a composite layout held together with a resin. It's a composite layout. When we would get skis in the fall to get ready to sell them, the first thing we do before we put them out on display is we take every single ski, we'd grab it by the tip and in the middle, put the tail on the floor, and we put our full body weight into it and flex it into a C shape. And when you did that, you would hear all kinds of cracks and pops as that ski flexed for the first time ever, because they wouldn't do it at the factory. And those were the stresses that were in there. It would do it that one time, it would never do it again. But we did it before we put them on display, because what we found is if we put a ski straight onto display and a customer did that, and they heard all that crackling, which was a normal part of a composite that is going to flex. The first time it flexes, it's going to give off acoustic emissions. The customers would get weirded out by it and think there was something wrong. So it's because an object gives off some kind of an acoustic emission, it doesn't necessarily mean it's a bad thing, right? Especially like a composite. The first time you flex a composite, there's going to be stresses in there that are going to have to be released, especially a composite made to flex, like a ski or something like that. But we would do that so that, our customers weren't doing acoustic emission inspection on the product before they bought it. Okay? And it was the manufacturers told us to do that. It was something that the manufacturers. So if you ever go into a ski shop or a snowboard shop, try flexing it, see if they do that before they put them on display. A lot of shops don't do that. You'll hear the crackle. It's kind of satisfying. It's like peeling the film off of a new television or something. Right? A little ASMR kind of thing. Short burst though. Okay, so here's a quick video, and then I'll go into a little more explanation in depth. So let's go some more details about acoustic emission. So here you can see it can be applied with nearly any material. right? Materials, when put under stress, all have the potential to make sound, whether it's in the audible range or in the ultrasonic range. Again, most of the inspection, most of the acoustic emission testing is done in the ultrasonic range. It doesn't mean that there couldn't be a component in the auditory range, like I was talking about with the skis crackling when you flex them. The problem with sound in the auditory range is oftentimes there's also a lot of noise in the auditory range. So one application, metals, is on bridges, put sensors on bridges. Where do you think the stress comes from on a bridge? From the cars or vehicles driving over. Every time a vehicle goes over it, it's going to flex, and it can produce, and there's a normal sound it may give, but then if there's a failure, that sound may change. Well, in the audible range, you also have things like tire noise, road noise, wind noise from the vehicles. And so that's not a great way to do it. But in the ultrasonic range, there's not a whole lot of other noises going on. And so that's why it's often done ultrasonic. Any idea where we might see this done on an aircraft? I think composite aircrafts in particular. What kind of things are going to stress or flex on a composite aircraft in flight? The wing spar or the wing structure, right? Those wings bend. Anyone that's ever flown has seen the wing, even on a metal airplane, you see the wings bend before the plane picks up. Or if anyone been in turbulence and seen the wings flex? Plane flaps. Anyone been in turbulence and seen the fuselage flex? So if you sit in the back of something like an A330 or a 777, you get in heavy turbulence, you can actually see the fuselage flex. If you look down the fuselage, you will see it flexing. It can move enough that you can see the flex. I've seen it on an A340. It was pretty cool. I pointed out, it was on the way to or back from my honeymoon. I pointed it out to my wife, who had been married to for like 2 weeks at that point, and she just about came apart on the airplane. But my explanation was, if it bends, it won't break. The other part, though, what else on the fuselage? What happens every time one of these transport planes flies, for the most part, to the fuselage? The pressurized, depressurized. Every time it pressurizes, it stretches a little bit. You might be able to pick up acoustic signatures from that. So metals, fiber reinforced polymer matrix, composites, more commonly known as fiberglass, carbon fiber, and Kevlar. Also things like concrete or wood. They've actually applied these to trees. If you have like valuable trees like redwoods and they want to know how the structure is internally as they flex in the wind, you've probably heard trees cracking on a windy day if you've been in the woods, right? So they're fast, continuous, real-time. Data acquisition is done by a computer recording device of some kind that also is going to often provide the analysis as well, because we can't just put your finger on something and feel the vibrations and analyze it as a human. That just doesn't work. But it's often, and most often, it's performed on objects that are in use, also known as in situ or in situation. Indirect access, so the sensors can be installed permanently, or they can be made removable. Removable ones often use like a coupling gel or some kind of a low-grade adhesive. Permanent ones are often epoxied right into the structure, for instance, or bonded directly to the metal. Not going to be welded on necessarily, but bonded with some kind of an epoxy usually. Epoxy works, certain epoxies work as a good bonding or coupling agent, just like gels can. And so you can, whether you install the whole system permanently and have constant monitoring, or install the sensors and then hook up the box that does the monitoring on a semi-routine basis. In the video, it did also talk about non-contact, using more of a microphone system. You can do that as well. That's more prone to extraneous noise in the atmosphere. It's going to pick up the noise that's being carried by the air as well. But minimal preparation is typically involved, especially if you have permanently installed sensors and permanently installed monitoring equipment. There really is no preparation at all. If you have permanently installed sensors, it may just be a matter of plugging in like a Canon plug or something and then turning the machine on. There are some disadvantages though. So the first, dynamic process. You can't hook it up to an airplane just sitting in the hangar and expect to get anything, right? You have to have some kind of material change in the material that causes it. It can also be temperature change. Things like, temperature changing, the expansion and contraction caused by temperature change can do it, but that's usually pretty minimal. Some of you may have experienced that if you ice fish or ice skate. Anyone ever been on a lake when it cracked? Sounds like a thunderclap going off. A big lake with heavy ice. So, things like that too can create the thing. So the flaws have to, whatever flaws you're finding, have to be prone to creating an acoustic event. Some flaws do not create any kind of an acoustic event, and so in that case, it wouldn't be helpful for us. Currently, it's primarily qualitative. It's going to be a situation where we know that damage maybe occurred, or, the monitors are on there, and there's a normal kind of a typical sound signature you get as the wing flexes or the bridge flexes, and then all of a sudden there's some kind of a change in that sound. Okay? What changed? What caused that change? Okay, if something changed, you may not know for sure what it was, how big it is, how structurally relevant it is. But you might be able to, with standardization, with standards and testing, you might be able to kind of get some estimate of the amount or even location. But to provide quantitative size, depth, etc., is proving difficult at this point. But there is a significant amount of research to try to, overcome these limitations because this is such this technique lends itself well to monitoring in service. And then the last one I mentioned already, sensitive to extraneous noise. So the theory behind it is that we talked about the emissions are the result of some kind of a change. The changes we're primarily interested in, from a conditional health standpoint, are things like cracks, slips, dislocations. Twinning is where the crystalline structure gets kind of bent, but you don't get an actual crack. Okay, the orientation of the atoms get pushed, or even the fibers kind of get slid against one another in a composite. It could be at the macro or micro level. Phase transformation, that's your freezing and thawing. Okay. And again, caused by application or removal. We can do it as the stress is applied, or as the stress is removed, or as the stress is applied and removed. A truck going over the bridge, the stress is applied and removed. The wings flex up and flex back down, right? The elastic waves, ultrasound travels through the part, and then it's detected and analyzed using the equipment we have. When we're performing acoustic testing, what we're looking for is an event or some kind of a useful signal. And so a single useful signal is known as a transient or burst signal. And this is typically a signal that occurs that's different than kind of the normal noise that's taking place. The normal noises an object's making, if we kind of know what those are, and all of a sudden it changes, or there's a short duration like a pop. You can think of it from in the auditory range as like a pop kind of sound. Right? That's what we're most interested in when we're performing acoustic emission. And the analysis that takes place is going to look at the waveform. And we'll look at this a little bit bigger in a second. But the amplitude is the highest, where it peaks. So this here is a single kind of auditory event. The threshold, you can see here there's a threshold is kind of the minimum. When the amplitude gets above a certain level, that's where we can say, yes, we're having an event, versus anything below the threshold, before or after this event would be your background noise, right? So you got to establish what is that background. Rise time, how long does it take from when the signal first starts to break the threshold till it peaks? Duration, when does it start to break that threshold until it stops breaking the threshold? Here's the duration at the end. Counts is based on frequency and that kind of thing. How many times, how many periods of the wave goes by within that within your duration. So number of signal crossings during the duration of an event. And then finally, the last one that most of these kind of probably make sense. Rise time, duration, counts, they're pretty straightforward. Mars is a word that most people probably haven't heard. That's the total energy. So roughly the area underneath the wave. Okay. So shown here, so this is if we were getting an output from a, like a piezoelectric sensor, right? The higher the displacement of the piezoelectric sensor, the higher the voltage. So this one's showing in voltage. It could also be signal amplitude if you're looking at it from like a sound perspective, like a decibel measurement. But remember that Mars is, if you kind of draw this line, this area, they're doing absolute value. You take the absolute value, it's kind of the area under all the peaks combined together, gives you Mars. That's the amount of energy released during this acoustic event right here. Okay. And then the other one that wasn't really in the list is well, I talked about count so many times. Does it go? You can also have measurements of, you can see here the frequency, the counts can be different sizes, different distances apart based on the frequency and the amplitude kind of together. So that kind of analysis takes place as well. So you see most of this analysis of one of these signals is going to have to be performed by some type of a computer or some type of an analysis tool that has the ability to run algorithms on this data. It's not something that's going to be necessarily intuitive where you can look at this. I mean, if you over time you'll see like experimentation where they kind of show these wave outputs and you're like, here's the thing, kind of like if you see a heart monitor, you can say here's the heartbeat, right? We can say here's where we had the acoustic event. So these are all, this signal is all affected though. It's going to be, the object's going to be stressed, flexed, heated, cooled, whatever. And somewhere you're going to have one of these deformations take place that's going to release acoustic energy. That acoustic signal, that wave or signal, is going to have to transmit or move through the part until it gets to our sensor, because we're not going to have sensors covering the entire surface necessarily. And so we have to take into account, when we're looking at these, when these signals, when these algorithms are being developed and analysis tools are being developed, you have to take into account things like wave and signal attenuation. How is the wave or signal affected? How is it particularly reduced by traveling through the material? So the intensity is going to be affected by the proximity of the sensor, as well as things like what's the geometry of the part between the sensor and the event location, where the sound originated, where the damage occurred. So the other thing you're going to have is something called geometric spreading. And that is as sound energy, transmits through a part, it starts at a point and then it spreads out from there, right? That same amount of energy is going to be spread over a bigger and bigger area. So the amount of energy or volume, if it's, when we're looking at 3D spaces. And so when it gets to the sensor, you're only going to sense whatever portion of that energy comes to that sensor versus the rest of the energy that travels through the part that doesn't have a sensor attached to it. So, if you have a plane, if it's primarily a flat surface, a thin composite layup, for instance, for each, point you double, if we have a, that's a good marker. Probably not the easiest to see. It's not super dark, but if we have a flat plane and we have an acoustic event that occurs centered, for each distance it travels, say here, if we travel to this distance here, that's going to be reduced by 30%, because here the sound is, distributed over that area. You go twice as far away, the sound's distributed over a much larger area, right? Because it's going to increase at the square of the distance, right? Or it's going to decrease at the square of the distance. So roughly 30% decay for every doubling of distance. If you're in a 3D object, if your part's 3D, and your thing takes place somewhere in the middle, right? It's going to be going out in every direction, going up and down and angle, right? So it's going to create spheres of detection. So for each doubling in distance from our point of origin, the amplitude of the total energy under there is going to be cut in half in a 3D structure. And that's caused by, a big portion of that is damping, right? The resistance to movement in the material itself, okay? And then the spreading of that out, right? So we're going to dampen the sound as we travel. The amount of energy is going to be spread over a larger area. And then finally, you can have wave scattering. And this is if you have uneven or rough surfaces or certain geometry, geometries that aren't cohesive throughout, or materials that aren't consistent throughout. Like a composite, again, you have all those layers and all those acoustic barriers between a fiber and the epoxy, and different types of fibers and that kind of thing. So if your material isn't homogeneous, it's going to cause a greater amount of scattering and that kind of thing. So that all has to be taken into account. So typically, this isn't something you can just go take sensors and apply them to something and say, I'm going to monitor it. There's going to have to be some study, some engineering, done beforehand to have an understanding of how that sound's going to spread. Other things, earlier I mentioned noise, right? Undesirable signals that are detected by the sensors. And most noise is going to be in the audible range. So again, working in the ultrasonic range, this tends to not be as big of a deal, but you can still get ultrasonic signals from things like friction, impact, loose hardware, right? Expansion and contraction, mechanical vibration from like rotation. Right? In the video originally, it talked about how rotating machinery is a little bit harder to do because oftentimes rotating machinery does give off, especially high-speed rotating machinery. The frequencies are going to match the rotational speed. You have a turbine engine running at 50,000 RPMs. It's going to give off some 50,000 or 50 kilohertz signal or sound, in addition to the audible sound we hear. So, negating noise effects can be done multiple ways. One of them is electronic gates. We say, you know what, we're putting this sensor on an engine that typically runs from 30 to 50,000 RPM. That means anything in the 30 to 50,000 kilohertz or 30 to 50 kilohertz range probably is going to be a result of machine operation. Maybe we look for signals in the 110 kilohertz range. You also have to be aware of multiples, right? If you have a 30 kilohertz or machine running at 30,000 RPM, it's going to probably have harmonics at 15,000 RPM. It's also going to have harmonics at 60,000 hertz, 60 kilohertz. So you got to kind of avoid some of those harmonic ranges as well. Physical distance. We know the rotating shaft is here. We're going to put our sensor over there. And then electronic filtering, things like signal arrival time. You know that there is, when there's an expansion joint at each end of a bridge, when a truck drives on it, you're going to get noise from the tires hitting the expansion joint. If I put my sensor here and the expansion joint's there, we know how long it takes for sound to travel. So we're going to ignore any burst signal that takes exactly this many, microseconds to get to the sensor, because that's the tires hitting the expansion joint versus a crack that forms somewhere in the middle. So you can filter out that way with, multiple microphones or that kind of thing. So the general system looks a lot like a ultrasound setup, in that you have a sensor, you have a detector that's going to have things like preamplifiers, filters, and amplifiers. Just like we can adjust the amplification on an ultrasonic tester by adjusting, that gain level is your amplification level. And you can also apply filters and that kind of thing on a ultrasonic tester. So we can apply those same kind of things here. Analysis, measurement, display, storage, and recording. Initially people used oscilloscopes. Simpler is even a voltmeter, looking at the voltage put out by a piezoelectric. But most common today is something that's going to be computerized, going to be able to run analysis while data is being collected, and it's also going to be able to store data over time. It's more important to do that than to look at it in just a snapshot. You got to look at snapshots over a period of time to kind of understand what's happening. There is a link there kind of to some demos. I'll let you do that through the slides if that's something you want to play around with. But here's a little bit more. So here we have our test object, an acoustic emission source. We have a sensor. We typically have a preamplifier near the sensor to boost the signal to send it to our instrument. And then the instrument itself is going to have the final amplifier used for performing the different functions there, used for performing measurement, recording, interpretation, evaluation. And then some kind of display or output, right? It's not useful unless we can look at it and realize something is happening. So your sensors, again, look a lot like a ultrasonic sensor for the ones that are attached, an ultrasonic transducer. So piezoelectric, some kind of coupling material. They may not have a wear plate. Again, this is an I can't find a dedicated acoustic emissions sensor, but they may not need a wear plate because you're not necessarily going to be sliding them over a surface. But there'll be some kind of coupling mechanism. Remember your piezoelectric element, it's going to be potted in a damping material to try to keep extraneous noise out, and then a protective case. Fixed or portable. So signal capture, the preamplifier is used to boost the energy in a raw signal in order to be able to transmit it over a distance. Because your analysis equipment's not necessarily located right next to the sensor. Right? You have sensors embedded all along a wing of an aircraft. The actual box that does the magic, so to speak, is probably going to be in an avionics rack somewhere inside the fuselage. So you're going to need these signals to make it to where they're going to be worked at. So the raw signal is boosted, increases signal gain, and it's typically placed as close to transducer. Often it's integral, especially in an installation situation. Once it gets to the, closer to the magic box, filters are going to eliminate extraneous frequencies or noise. High pass filters out higher frequencies than your desired. Low pass filters out lower frequencies than what you desire. If you combine them, a high and a low pass, high above, anything above here, get rid of, anything below here, get rid of. Those are called a band pass. It's going to allow this band in the middle to pass through. So high pass, low pass, and band pass filters. And then it goes into the actual, what would be the main amplifier. The clean signal is then amplified to a level where we can perform analysis on it to make it big enough to see, big enough for the algorithms to see. What's more common, so a little bit better, display looks like this. Separate them, put that preamplifier near our sensor, put the main amplifier near our measurement circuitry, and then add an output at the end where we can see or be told. And then, the next step beyond that is they're often grouped together. So you may have multiple sensors with multiple preamplifiers. Again, this is what I was talking about where, like in a wing, you might have multiple sensors along the spar. On a bridge, you might have multiple sensors along that. On an engine, we had vibration monitoring on engines, which is a form of acoustic emission, or vibration, or it would also do physical vibration, so going down into the physical movement category. You would have them at different orientations in order to capture things like vertical and horizontal deflections. Right, you can put the sound sensors in different orientations to find different phases in the sound transmission. So then you can combine that into processing, storage, operator input, output, screen displays, printer output. Right, so these machines are much more complex than just a single sensor with a single operating box. The box is going to tie together many sensors to give you a bigger picture of what's going on. Ultimately, we want to know, the biggest thing was where is the sound coming from and what does that sound mean? So first, to figure out where we need to, having a homogeneous material, a single metal made out of a single alloy, right, is a lot easier than a non-homogeneous material, like a composite, where you have a lot of acoustic interfaces there. Also things like regular shapes or structures, spheres, cylinders, cubes, or boxes are going to be a lot easier than all kinds of funky shapes. But in aviation, we know the whole purpose of things like, composites is that we can make them into very complex shapes much more easily than we can with metal components. That's a big advantage of going to composites. They're light, they're strong, and they can be formed in all kinds of different shapes. So it becomes more difficult, but it's not impossible. It just takes some research, and you gotta, there's experimentation that takes place ahead of time. So composites in irregular shapes, hence airplanes, are more difficult than square boxes. And there's three primary methods used for determining location: linear, zonal, or point. So linear is the most simple. You have to have two sensors for a linear test. And what you're doing is those two sensors are essentially listening for the same signal, the same event. And you're looking at the waveform of the event to kind of get some idea of how big of a crack formed. How fast did it form? Did it grow, or was it a real quick and then done, or is it continuing to happen? But then to figure out relative distance is, with two sensors here on the left, this diagram on the left, the sensor on the left is going to pick up that signal first before the sensor on the right. And so speed of sound is linear through an object. So you can essentially compare, what was the distance, if the sound, it'll hit each sensor equally at the midpoint, and what's the time it took to get to each one. The other element of that is it will likely be a stronger or more powerful signal being received by the left-hand sensor than the right, because you have less attenuation. There's less material that's going to damp that sound as it travels through it. So the sound's not going to be attenuated as much. So you'll get a stronger signal on the left than the right. On the one below, the blue one, you probably get a stronger signal, an earlier signal on the right-hand sensor. Right? You can see this cracks a little off center when a force is applied, where this block, the idea here is the force is in the middle and it's being held up on the two ends. Just kind of an illustration of that. So this gives you a straight line distance between 2 points. But if you put this on a two-dimensional plane, the problem becomes you may not be able to figure out, you'll be able to figure out its position on a line, but you won't be able to figure out a position on a 2D plane. So if we look at a 2D plane here, if I have sensor A over here, and I have sensor B over here, right? If a crack occurs here or here, you're probably going to see a relatively similar signal, right? It's not going to look too much different, because the distance to here and here is the same, the distance to here and here is the same. You're not, so you'll be able to figure out, okay, there was probably a crack somewhere along that line, but you won't be able to say, is it near the top of my drawing or the bottom of my drawing, right? So then the next one is called a zonal, and this is a 2 or 3D array. Now, this is a little bit different. There's going to be another one is point location. Okay, zonal is we have multiple sensors, and this is particularly materials with high attenuation. The sound's not going to travel very far through it, or it's going to be attenuated in a relatively shorter distance. And so what's happening here is each sensor is responsible for monitoring one zone. So if a crack occurs in this center zone, which has sensor 4 in it, all we're really going to sense it at, or it's going to be detected, is by sensor 4. We're not going to be able to reliably detect it at sensors 1, 2, 3, 5, 6, or 7. Okay? So zonal means we can pinpoint where the flaw occurred within a zone. So essentially what happens is it doesn't matter if the flaw occurs near this top area, or the bottom, or the left, or the right. Sensor 4 will pick it up. Nothing else will reliably sense it. So we know our flaw is somewhere within this center cell. But we can't position it beyond that. Okay. Again, areas that have high attenuation, especially larger areas, this may be the only thing you could do without having to put an excessive number of sensors. If you did want to do the next thing, which is be able to triangulate a signal, you would have to put a lot more sensors here. And some materials don't lend themselves to that. You'd have way too many sensors. The cost would be too high for the gain. Okay. And then, the source location, if you have a sensor array with at least 2 sensors, we talked about 2 sensors, you get linear determination. With 3 sensors, you can start to get planar determination. So 3 sensors that pick up the same signal, we can triangulate it on a plane. But in a 3D object, it could be, we may not be able to get vertical distance, right? 3 sensors on top. We could say, it could be, we could say it's here, but it could be here, 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 just anywhere on that. So to get a true volumetric determination, a determination within a 3D object, we would need to have a 4th sensor. It works like GPS. GPS signals use the same thing here with radio waves. You have to see 4 GPS satellites in order to get altitude. With 3, you can get your position on the surface of the Earth. So measuring distances, differences in arrival times and energy, and if you can have even more sensors, you can get more accurate. I think many GPS receivers work somewhere, like phones, I think they're looking at anywhere from 4 to 16 satellites simultaneously. So the more sensors that can pick up a sound, the better you can triangulate and the better you can locate that signal more accurately. But the trade-off is more sensors means more cost and more complexity. And you have to be able to analyze that. And so you can actually get very accurate location determination in geometrically complex parts when you have multiple sensors. And it's looking at a combination of how long does that, this source sound, how long did it take to get to sensors 1, 2, and 3? And also, how much was the signal attenuated when it arrived at sensors 1, 2, and 3? You can kind of use that as a combination of the two. Now, I've primarily talked about passive acoustic emission. There are acoustic emission testers that allow you to do, that are active as well. These are typically used in experimental or developing systems, where we can have a signal detector and then a signal generator. So you can see this looks a lot like an ultrasonic tester. And the signal detector, it's fed in, information is fed into the detector to tell it that you've put a signal output. Okay. Again, more of an experimental controlled environment versus the ones that are being used in practice. Or this could be a specific test you perform in a hangar environment or a shop environment. So for aerospace, as I've alluded to, permanently attached sensors are out there. There are aircraft that have these, and they have onboard computers that are constantly monitoring. It typically doesn't show up on displays. It's not something that the pilots are going to see. They may, bless you, the pilots may not see it, but it'll be logging in. It'll be a maintenance log where you as a maintainer can go download the information. You can look at it and give you some idea of health of that structure of that aircraft. Okay. Wing spars, landing gear trunnions. When's a good time to monitor a landing gear trunnion for sound emission? When do you think? What's that? When you smash a 100, 200, 300,000 pound aircraft into the ground and put a ton of stress on the landing gear, right? Hopefully on top of the landing gear on the ground. But, so that engine mounts, also impact detection. These were first used, one of the first applications was in the United States shuttle fleet after the Columbia accident. So Space Shuttle Columbia on liftoff had a chunk of foam come off the big orange tank and it hit the leading edge of one of the wings. And when they were done with their mission, when they were re-entering the atmosphere, that foam chunk had actually punched a hole in the leading edge. And when re-entering the atmosphere, that hole allowed hot gases in, and it destroyed the structure and caused the breakup of the Space Shuttle Columbia. So when the space program resumed after that, the shuttle program resumed, they had installed acoustic emission sensors on the shuttles in order to determine if those same kind of impacts had occurred on liftoff. If that was the case, what kind of a rescue mission might be able to put in place rather than bringing the crew back down in a damaged vehicle. Fan blades, engine vibration, fluid flow and leakage. I do have a video on this. I'll show it next time. Here you can kind of see a demo of acoustic emission sensors placed along a wing spar. So